A furnace can hold heat far past 1,000 degrees, and somewhere inside that glow a temperature sensor still has to give an honest reading. Standing between that sensor and the fire is a single piece of ceramic, closed at one end, and the accuracy of every reading depends on it holding its ground. Silicon carbide earns its place here by handling several harsh conditions at once. In air it stays dimensionally stable up to around 1,650 degrees Celsius, and in a controlled atmosphere it tolerates more still. When the hot surface meets oxygen, a thin film of silica forms and seals the material against further attack. The reason it resists oxidation through long service. Acids, alkalis, and molten non-ferrous metals struggle to corrode it. Its hardness sits near the top of engineering ceramics, so abrasive dust and slag wear it only slowly. And it shrugs off the sudden temperature swings that crack lesser materials when a cold tube meets a hot zone. The reason this tube is silicon carbide rather than another engineering ceramic comes down to how heat moves through its wall. At room temperature it carries heat at roughly 130 watts per meter Kelvin, about 4 times dense alumina, which sits closer to 30. Heat from the furnace must pass through the closed wall before the thermocouple inside can feel it, and the rate of that transfer is set by the wall's thermal resistance. Thinner walls and higher conductivity both lower it. A material that conducts heat this well lets the enclosed sensor reach the true process temperature sooner, so the gauge follows a real change instead of trailing it. In a process where a few degrees decide quality, that lag is exactly what the material is chosen to remove. Sizing usually starts from a handful of common combinations. A 16 mm outside diameter pairs with an 8 mm bore and runs up to about 550 mm. A 22 by 12 tube reaches past a meter. A 28 by 16 extends to roughly 1,200 mm. Wall thickness on these sheaths commonly lands near 5 to 6 mm, enough to carry the mechanical load without holding back the heat. Beyond the common sets, outside diameters reach toward 300 mm and lengths toward 3 meters for furnace wall mounting, the closed tip rounded as standard and pointed on the largest bores. Bore, wall, length, and the seal at the closed end all get matched to furnace depth and the sensor the tube must carry. In a non-ferrous melting furnace, the tube goes straight into liquid metal held above 700 degrees, and it has to read that bath without dissolving into it. The same corrosion resistance that shrugs off acids keeps molten aluminum and zinc from eating the wall, so the sensor stays clean and the reading stays honest heat after heat. The material's high conductivity means the moment the bath drifts, the gauge moves with it, which is what lets an operator hold a casting temperature inside a narrow window. The closed end keeps the thermocouple out of direct contact with the melt, and the resistance to thermal shock lets the tube drop from cool air into glowing metal without splitting. Pulled out, cooled, and returned for the next heat, it keeps both its shape and its accuracy across cycles that would finish a metal sheath in weeks. Long after a metal sheath would have slagged away in the bath, this one comes back out holding the same shape and the same number, which is the whole point of reaching for ceramic in the first place.